Okay, so two identical objects, the hotter object gives off more energy. I'll consider a question a little bit more tricky. Two objects at the same temperature, but one object is twice as big as the other, which object will give off more total light? And it may help you to substitute the word heat for light here as you think about this. Lots of us have stove ranges where we have little ranges and much bigger ranges. So which range heats more effectively? Pause, think, guess, and yes, it's the bigger object. So the total energy output, the luminosity, is affected by both size and temperature. Specifically, it goes as the area, which is a length squared dependence, and something called the flux, which depends highly on temperature. The actual mathematical formula is that, but this is astronomy, so we use proportions. The luminosity goes as the radius squared and the temperature to the fourth. So temperature is actually a stronger power dependency than radius, even though the size of the star matters a lot because the square is no joke. So you're observing two stars. Star A is almost twice as hot as star B, but star B is 100 times more luminous than star A. So A is twice as hot, but B is 100 times more luminous. Going back here, temperature goes as the fourth, radius goes as squared. Okay. Star A is twice as hot, but star B is 100 times more luminous. So pause, think, which star is bigger? The answer is definitely star B. If it's putting out more total energy, but it's cooler, then it's got to be huge. So back to thinking about length, area, and volume. When we're dealing with luminosity, it's the area of the star that matters because it's just the outer skin that's glowing and releasing energy out into outer space. Now, there's light, there's photons all throughout the star, but we only see the photons that leave the outer surface. Now we're going to do some activities. I will again ask you to pause the video and think about these as we go. Whoops. So exercise 1. Imagine you're comparing 5 electric hot plates of different sizes and temperature. The temperature of each hot plate is indicated by a shade of gray, such that the lighter the shade of gray, the higher the temperature of the hot plate. So pause, rank the surface area of these. Then rank the temperature of these. Then rank the total energy output of these. So pause, rank the temperature, the surface area, the total energy output. And now I'm going to do it for you. As far as size, that's pretty easy. D is the smallest, C and B look tied, C, B, and E look tied, and A is the largest. So A, comma, B equals C equals E, comma, D would be largest to smallest. As far as hottest goes, D looks like the hottest to me, then B, then C, then E, then A. Then total energy output is harder to figure. So now we have to think both about temperature. Oh, sorry, I did the temperatures backwards. And I'm being recorded. A is the hottest. A and E are tied at the hottest. And then C is the next hottest. And then B and D are the coolest. My apologies. So as far as energy output goes, we're lucky in that the largest objects are also the hottest objects. So I can say that A has the greatest energy output, then E, then B, then C, then B, then D. So from greatest energy output to least energy output, I have A, E, C, B, D, because temperature matters and size matters. Higher the temperature, more energy output. Bigger the size, more energy output. Now, I'm going to show you your very first HR diagram, and it relates the luminosity, the total energy output versus the temperature. Rank the temperature of the stars from hottest to coldest. Then rank the luminosity of the stars from greatest to brightest. Rank the surface areas of the stars from largest to smallest. This takes some thought, and I'm actually going to pause on this. I'm going to do this after I introduce HR diagrams. Sorry, back to the slides. We shall return to that, but I want you to see HR diagrams a bit before that. So it's hard to measure the mass of a star because you can't get out there and put it on a scale. But we have all these methods by which we can work backwards and figure out the luminosity of a star. Some stars are very dense and some stars are not. So some stars are like marshmallows and some stars are like a brick of iron, basically. But you can somewhat infer the mass by looking at the gravitational influence of the stars. Newton's and Kepler's laws explain how orbits are caused by gravity. So if we can find two stars that are in orbit around each other, we can measure the properties of their orbits and determine their mass. When two stars orbit a common center of mass, they're called binary stars. The location of the center of mass is indicated by a red cross. So imagine two stars trying to balance on a giant seesaw. If you can get them to balance, you know where the center of mass is, so you know what the relative mass of one star versus another is. It's the balance point. This point is always closer to the more massive star. So if D1 is 1/3 of D2, then the mass of the green star is 3 times the mass of the yellow star. How can we use the orbits to determine the mass of the stars? Well, you look at the spectrum. Because the star is blue shifted when it's swinging towards us and red shifted when it's swinging away from us. This only works if the motion is towards or away from the Earth. If we're looking at the star system flat on and the motion isn't towards or away from the Earth, then we can't use this trick. And so quite often we can't use this trick. But when we can, we fully exploit it. So you measure the velocity of the stars and the Doppler shift in their absorption line. The more massive star is closer to the center of mass and thus travels a smaller distance and always moves slower. This kind of binary star system is called a spectroscopic binary because you determine that it's a binary star system by looking at its spectroscopy. Let me get these applets loaded. So in our solar system, even though we don't have a binary star that we know of, the planets are going around the sun and we are tugging on the sun by a tiny bit. This is a big part of how we detect extrasolar planets. Like if you include Mercury, then Mercury will make the sun move by a super tiny bit. Even though Mercury is in very close, it is not very massive. Include the Earth makes the sun move by a super tiny bit. But go to Jupiter, which is pretty far out, but so massive that Jupiter is actually making the sun twirl around in a circle. The center of mass for Jupiter and the sun is outside the sun's own body. So if we were on a very distant solar system, looking at, if we are in a distant star system, looking at our star Sol from that distant star system, we will be able to detect Jupiter pretty easily because Jupiter is wrenching the sun around in a circle. Now, the sun's doing a lot more to Jupiter than Jupiter is doing to the sun. The sun holds Jupiter in an orbit, but that's still a noticeable motion. This is why the biggest exoplanets we found, that's why the first exoplanets we found are the biggest exoplanets. And then none of the other planets do too much. We will be able to detect Saturn, but Uranus, Neptune, Pluto. If you include every planet in the solar system, then the sun's motion becomes quite complicated. And you would have to work backwards to figure out what in Earth is going on, how many planets are here. And you'd hope like crazy that occasionally the planets would get in between the sun and us so that we'd see the sun dim. And that would give us a good idea of how big the planets are. Speaking of which, let's talk about visual binaries. There are stars that are close enough that they actually look like separate stars. They got to be pretty darn close, but it happens. We also detect binary star systems from eclipsing binaries. This lets us not only detect binary star systems, but occasionally lets us detect other planets. When a star gets in the way of the light from the other star, we see the light signature dip. Star goes on the far side, we see the light signature dip again. We only can detect eclipsing binaries if the system is set up in such a way that we're looking at it edge on. Like this, stars have to physically get in each other's way from the point of view of Earth for us to use this technique. Can an eclipsing binary system also be a spectroscopic binary? Pause, think. The answer is yes, why not? Here I see these stars as being separate things. Over there is the Earth. We're looking at this edge on. And they're close enough that you see them as separate objects. Can you explain what you're seeing here in terms of the Doppler effect, which is another piece of information we use to get info on stars? So think about it. I would like to send you in discussion rooms, but it's a recorded class. And hopefully you can explain it. When B is approaching us, the light from that absorption line is a little blue shifted. When A is receding from us, the light from that absorption line is a little red shifted. So slide 1 and slide 3 show blue shifting and red shifting respectively. But with 2 and 4, that motion is not towards or away from us. So no blue shifting, no red shifting. It's the same absorption line. So we don't see any Doppler effect. Final review of moon phases. I would normally do an activity with you here. We'll talk about when does a waning crescent moon rise, when does it set, when is it dead overhead. Since there's nobody in the classroom to do that activity, I just want to reiterate and say, know how to figure out moon phases. Go and look at those applets if you'd like. So measuring the properties of stars is the first step. Looking for patterns and data is the next step. In 1911, 2 astronomers independently plotted the luminosity, the total energy output of stars versus their temperature. And they created a fairly famous plot that's useful for understanding the properties of the stars. This plot is called the Hertzsprung-Russell diagram, or HR diagram. It's what everybody says. This is not an HR diagram. This is an intro to the idea. So imagine you measure the heights and weights of a large group of human beings. Most of the points lie along a diagonal line. If you are taller, you probably weigh more. There are some anomalies. Occasionally you get people that are not very tall and who weigh a lot. And occasionally you get people who are very tall and are very skinny. But in general, the taller you are, the more you weigh. This is a pattern of noticeable behavior that stars abide by as well. So most stars go on a diagonal slash when you plot their luminosity versus their temperature. Note that the x-axis is backwards from the way you might naively expect it to be. Low temperatures are to the right, high temperatures are to the left. And the class of stars on that diagonal slash on the main sequence are stars that are still relying on burning hydrogen as their fuel. Everything off of the main sequence is either burning some other element or is dead or something more complicated is happening. So from the HR diagram, you can knock out size of the stars, you can knock out the mass of the stars. In general, the hotter a star is, the more massive it is. And here's another analogy for you. In life on Earth, in general, the bigger your body is, the longer you live. That's how it works. And if you take that concept and you lay it over an HR diagram, there's a pretty close corresponding to it. So super tiny objects do not live very long. Super big objects live a really long time. Now, here's how not the same size stars are when on the HR diagram. M stars are teeny tiny in comparison to O stars. The hotter you are, invariably, the bigger you are. And if you're on the main sequence, the hotter you are, the more massive you are as well. When a main sequence star is less massive, it is smaller, cooler, redder, and less luminous. When it's more massive, it's larger, hotter, bluer, and more luminous. So main sequence stars are the ones that are burning hydrogen and helium in their core, nothing else. As soon as the situation gets more complicated than that, they stop being main sequence stars. So stars not on the main sequence are going through their death throes. They become giants, supergiants, or else they're completely dead and they're white dwarfs. And there's an HR diagram with real stellar data. So here's the HR diagram. On the y-axis, you have energy output. And on the x-axis, you have temperature, but it's backwards of what you might expect. The redder stuff is over to the right, and so the cooler stuff is over to the right, and the bluer / hotter stuff is over to the left. Now that we've done a little overview of HR diagrams, let's go back to those slides that I got gun shy about earlier because I wanted you to have more of an introduction. So go ahead, pause. Well, don't pause yet. Rank the temperature from hottest to coolest, rank the luminosity from greatest to least, and rank the size from greatest to least. Come up with all your answers, then unpause. So for temperature, that's a measurement off the x-axis. A is hottest, then B, then C, then D. For luminosity, for energy output, all of these things are in a line. That line lines up with the 100 on the y-axis. So they all are putting out 100 sun units of energy. That means they're all tied. A is as luminous as B, is as luminous as C, is as luminous as D. They're all putting out the same amount of energy. What then can you infer about their size? Well, if D is not that hot and A is super hot, but they're all putting out the same amount of energy, then D must be huge and A must be teeny tiny. So D is much bigger than C, is much bigger than B, is much bigger than A. Now let's consider the same thing, but somewhat backwards. Rank the temperature, rank the luminosity, rank the size. So pause, get your answer, unpause. All of these stars are lined up in terms of temperature. They all are about 1500 Kelvin. So A has the same temperature as B, has the same temperature as C, has the same temperature as D. But as far as energy output goes, A is producing by far the most amount of energy, then B, then C, and D is producing the least energy. So what does that mean for the size? A must be huge. B is smaller, C is smaller yet, and D would be the tiniest. One last go through, we're going to rank the temperature, rank the luminosity, rank the size. So pause, get your answers. A is the hottest, then B, then C, then D. But D is the most luminous, then C, then B, and A is putting out the least amount of energy of all of them. So D must be enormous. C is the next biggest, then B, and A would be the smallest. Notice this is backwards from the slash that main sequence stars occupy. You would be hard pressed to find a group of stars that actually match up with this. But being able to read it means you can now read an HR diagram and infer about the size of stars from the relative positions. Oops, not what I wanted to share. Well, I guess that's all I got. So back to where we were. So there's an HR diagram with real stellar data. Here again is a picture of a field of stars, just to really emphasize stars do have different colors. The blue-white stars are much hotter than the sun. The red stars are much cooler than the sun. On average, the stars in this field are about 25,000 light years away. And the width of the field is about 13.3 light years. This is a pretty dense cluster of stars. And here's an HR diagram with some stars that you may have actually heard of. Barnard's star is going by us. It's too faint to be seen without binoculars. Proxima Centauri is a star that we're not entirely sure if it's part of the Alpha Beta Centauri star system or not. Alpha Centauri is very close to a twin of the sun. And then Procyon, Vega, Sirius, Spica, all main sequence stars, all very bright. Oh, excuse me, all very luminous. The stars Arcturus, Aldebaran, Antares, and Betelgeuse are all in their death throes. So they have become giants and supergiants, and they are on their way out. And I will teach you in what way they die later. Here is a more active example of how an HR diagram works. So we've taken some star field, and we're going to sort the stars by temperature first. So the hotter, bluer stars on the left, the cooler, redder stars on the right. And then we're going to sort them by their total energy output. So luminosity, most luminous at the top, least luminous at the bottom. And so I can see right away, this star cluster is kind of old. Like there's a lot of giants associated with it. And that's how you analyze an HR diagram and figure out what a stellar neighborhood is like. Oops. When stars are just burning hydrogen, they're on the horizontal slash that goes from the top left to the bottom right. Once they start burning the different elements, or exploding, they behave very differently. Gaia is doing very good work with mapping nearby stars. So here's more beautiful and interesting data for you to consider. Okay. So here are HR diagrams of what this is supposed to be showing me is HR diagrams of different star systems. And that is not what I'm getting. And I'm not sure if it's my browser or what. Huh. Let me try a different browser real quick just to see if that works any better. And in the meantime, I will show you some HR diagram data on a different idea, which is variable stars. So there's a lot of different types of variable stars, but the thing they have in common is that they oscillate in temperature and in luminosity. And this almost always means one thing. The star is not in equilibrium with itself. Like it is in some funny stage of life where the force from gravity and the light pouring out of the core are not in a good balance. And consequently, it's shrinking and growing in size and its temperature is fluctuating. These are certainly not stars that you would like to be living around because you'd like your star to have a nice defined size and not oscillate in temperature or in how big it is, lest your planet suddenly find itself inside of the surface of the star. Much more about variable stars later because they are super useful to astronomers. We think each of these colors represents a really similar type of star. And so whenever we find them, we get excited and we try to work backwards and infer all kinds of things about how far away objects are, assuming that most classes of variable stars behave the same as other members of the same class. Okay. It is working on Firefox. So I will go over to Firefox. So here are the stars that Gaia is looking at. And it is measuring the color and is looking at a bunch of different star clusters all around here. Putting all that star cluster together, you get this. You get an HR diagram. So there's the full main sequence, and there's a cloud of giants. And you notice that there's very few white dwarfs, and the reason is that it's almost impossible to see a white dwarf. We can infer their existence, but they're putting out almost no light. So there's a young, vibrant cluster, which still has a lot of blue stars. Blue stars blow up and die much faster than red stars. There's a very old cluster where the blue stars have mainly trailed off. Young cluster, middle-aged, so on and so forth. As a cluster ages, the blue stars go first, then the greenish stars, then the yellowish stars, all of them swelling up to become giants, and then eventually turning into white dwarfs, or into even more exotic objects than white dwarfs. All right, almost through. Planet of the day is Earth. Because the sun is warming up, over the next 50 million years, the temperature on Earth will rise unless we control our atmosphere to prevent that. So to give you a sense of scale, hominids were making tools about 2.5 million years ago. So, you know, we've got a while. Halfway through that process, about 25 million years from now, the Earth will boil away all of the water vapor on it. And all the water will be destroyed on Earth exactly the way it was destroyed on Venus. Dinosaurs went extinct only 65 million years ago. So if you think about it from that perspective, this is going to happen in not too long. So the nice thing about this is that if humans can solve global warming, that is kind of a baby step towards dealing with the heating up of the sun. This is not an insurmountable problem. We will not necessarily have all life on Earth go extinct in 25 million years, but it's going to take technology to stop that from happening. Our moon is a result of something about Mars size hitting the Earth a while ago in the very early solar system. We've tested isotopes from the moon and confirmed that much of it used to be Earth's crust. This is a big part of why metal is so easy to mine on Earth, because what would normally be our crust is in orbit around the planet. The moon's core is mildly off-center because it froze out after the collision so fast that the mass couldn't completely organize itself dead in the core. And I don't actually remember what this YouTube link is. And so it'll be an exciting adventure for me as well as you. Looks like it's just a close-up. Yeah, it's the moon. Well, our moon's a very special object. We're lucky to have it for a bunch of different reasons. It keeps the Earth's axial orientation relative to the ecliptic pretty stable at 27 degrees. It's full of all kinds of useful resources for us. It gives us the tides, without which life very well might or might not exist. It shortens the length of Earth's day for us through interaction with gravitational and frictional forces. We think that when the moon was first knocked off the Earth, the amount of time it took the Earth to have one day was about 8 hours. So the Earth spanned once every 8 hours. And the moon's been lengthening the day ever since. If it had enough time, the moon would eventually make the length of Earth's day 26 days. But it's not going to have enough time. The sun's going to swell up into a supergiant before that happens. However, when the meteorite that killed the dinosaurs hit Earth, the day was 23 of our current hours long. Now it's 24. Eventually it'll be 25, then 26. So we can thank the moon for our nice, reasonable length of time that we spend in daylight and in starlight. And that's it. And I'm going to hope fervently that there haven't been any technical issues. There should be 3 files that get uploaded to represent this lecture. And I will encourage everybody to watch them. And I'll also download them and put them on YouTube if I can manage that technical feat, which I should be able to, just to make it even easier to access them. Hope everybody has a great week.